Chapter 3 is probability. And then in Chapter 4, we tie the probability that we learned in Chapter 3 back with some of our previous concepts that we've done in statistics. Probability experiments. A probability experiment is an action or a trial through which specific results are obtained. What this means is if you were to actually flip a coin 100 times and record the results, you would be performing a probability experiment. The result of a single trial is called an outcome. So the first time you flip the coin and record it, that's your first outcome. And if you take the set of all possible outcomes, it's called the sample space. So when you're flipping a coin, there's only two possible outcomes. So the sample space would only consist of heads or tails. An event is a subset of the sample space, and an event may consist of one or more outcomes. And we'll talk about that more when we get to example 2. The first example is just to identify the sample space of a probability experiment, and then we're going to determine how many outcomes there are. This is a survey that consisted of asking people their blood types, so they can be type O, A, B, or AB, and then they had to include whether they were Rh positive or negative. So the way we're going to do this is we're going to create what's called a tree diagram. And in the tree diagram, you come down and ever how many options you have for the first choice, that's how many branches you're going to have on your tree. So we have 4 blood types. So I'm going to come down and I'm going to come off of here and I'm going to have 4 blood types. So a person can be O, A, B, or AB. And then from there, they asked the people whether they were Rh positive or negative. So off of each blood type, you have 2 more possibilities. The person can be O positive or O negative. They could be A positive or A negative. So off of each of the blood types, you have a positive or a negative. And when you get finished, you count the bottom row, and that would be your number of outcomes. So there are 8 possible outcomes. The way we list this is it is a set. The sample space is a set. So we are going to put the little curly braces here for the set of all possible outcomes. So our outcomes could be O positive, O negative, A positive, A negative, B positive, B negative, AB positive, or AB negative. And that would be the sample space. And then, of course, you just count those up and there's 8 possible outcomes. And that's how you create a sample space. A simple event is an event that consists of a single outcome. So in other words, when they give you the event that you're looking at, there's only one possible way for that event to occur. So for example, rolling a 3 on a 6-sided die would be a simple event because there's only one way you can roll a 3. Only has one outcome. But if you said rolling an even number, there would be 3 different ways that you could roll an even number because you could roll a 2, a 4, or 6. So that would have 3 outcomes. So a simple event has only one outcome. And that's what we're looking at on example 2. Determine the number of outcomes and decide whether or not it is simple. For quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So a specific part would be an exact part. So like if you had labeled all the defective parts and you said I wanted the probability of choosing part C, then there's only one way to choose that specific part. So this would be only one outcome, which would mean this is a simple event. On number 2, it says you roll a 6-sided die. Event B is rolling at least a 4. Well, at least a 4 could be a 4, a 5, or a 6. So there are 3 possible outcomes here. And since there's more than one outcome, it's not simple. The second part of this lesson is the fundamental counting principle. This is a way to determine how many different ways events can occur without actually having to draw a tree diagram every time. And I will draw a tree diagram on this next example to show you how it works with the counting principle. But then on the example following that, we'll look at one where it would be almost impossible to draw out all the possibilities. So the fundamental counting principle allows us to figure out the number of different ways something can occur without actually drawing it out. So the fundamental counting principle says if one event can occur in m ways and a second event can occur in n ways, then the number of ways the two events can occur in sequence is m times n. So you have 6 flavors of ice cream and 10 different toppings. And how many ways can you choose one flavor of ice cream and one topping? So you had 6 ice creams times 10 toppings would be 60 different ways you could choose one ice cream and one topping. That would be an example of the fundamental counting principle. And this rule can be extended to any number of events. So on the example we're looking at on 3, we have a car manufacturer, a car size, and a color. So we have 3 events that we're picking from. So it says how many ways can you select one manufacturer, one car size, and one color. So according to the fundamental counting principle, I have 3 manufacturers I can choose from. I have 2 car sizes to choose from, and I have 4 colors to choose from. So I should just multiply 3 times 2 times 4, and that would be 24 ways. So there would be 24 different car size and color combinations that I could end up with. Now we're going to draw a tree diagram to show that this is how it works. So you start and you come off with your first one, and you have 3 different manufacturers. So that would be our first set of branches. And then off of each of those, you have 2 car sizes that you can choose. So you can choose compact or midsize. And then off of each of those, you have 4 color choices. So for each one of these, you have white, red, black, or green. So you would write that in going across each of these. And when you get finished, you can count these up, and there's 4, 8, 12, 16, 20, 24. And that shows that there were 24 possibilities. If you were going to write out the sample space, which they don't ask us to, they typically won't ask you to write out a sample space if it's a huge one, but I'll just show you kind of the beginnings of it. If you were going to write out the sample space, it would be Ford, compact, white. Or you could have Ford, compact, red. And you would just keep doing that until you listed all of the possibilities. And of course, there would be 24 of those when you got finished, but that would be how you would write the sample space. You would actually write out all the different possibilities. On example 4, this is one where it would take forever to try to write out all the different possibilities, because what they're asking us to do is look at an access code for a car security system, and it has 4 digits. So this would be like choosing the 4 digits for your screen lock on your phone. And what's the possibility somebody's going to choose the exact sequence that you picked when there's so many different choices? And this is going to show us how many different possibilities there are. So it says that we can choose any digit from 0 to 9. Okay, the first thing I want to point out is a lot of people, when they see 0 to 9, they say you have 9 different digits. It's actually 10, because you count the 0 and then 1, 2, 3 all the way up to 9. So you have 10 options for your digits, unless something in the problem specifies that one of the digits can't be a certain number. So when we figure these out, we're looking at how many choices do I have for the first digit. They're not asking you to pick the first digit. They're saying how many options are there for the first digit, how many options are there for the second digit, and so forth. So on number 1, it says each digit can be used only once and not repeated. So when I pick the first digit, I can pick any one of those numbers 0 to 9. So I have 10 options or 10 choices. That doesn't mean I'm choosing 10. That means I have 10 choices. And then we multiply that by how many options or choices do I have for the second digit? Well, since it says they cannot be repeated, I now only have 9 choices left. So for example, if I chose a 5 for the first digit, I can't use a 5 again. So now I have one less choice. And then for the third digit, I can't use the 2 I used before. So I now only have 8 choices, and then I have 7 choices. So the total number of choices I have when you multiply that is 5,040. So you can imagine how long it would take to try to draw this out with a tree diagram. You would have, you're coming off of here, you would have 10 choices to begin with. And then off of each one of those, you would have how many choices are left. So you'd have to have 5,040 when you got finished. So that would take forever to try to draw. On number 2, it says same thing, 4-digit access code, but every digit can be repeated. So that means I have 10 choices for all 4 digits. I can use a 9 all the way across, a 5 all the way across. I could use 2 5s and 2 4s. I have 10 choices for each one of the digits. So that would be 10,000 ways to create an access code, or 10,000 different access codes that are possible. And then on number 3, it says each digit can be repeated, but the first digit can't be 0 or 1. So if the first digit can't be 0 or 1, that leaves us only 8 choices for the first digit. But then the rest of the digits can be anything. So I have 10 choices for the second, the third, and the fourth. So I would have 8,000 total ways to create that access code. On part 3, we have the types of probability. And the first one is the classical, or what we call theoretical probability. And this is what you would expect to happen. So when you're doing this, this is used when an outcome in a sample space is equally likely to occur. And the classical probability for an event is given by the number of outcomes in event E divided by the total outcomes in the sample space. But this would be when, like, say, if you're rolling a die, then each number on the die is equally likely to occur. So typically you would say, well, there's a 1 in 6 chance of getting any one specific number. So that's theoretically, that's what should happen. If you wrote it 6 times, theoretically, you would get each one of the numbers once. So theoretical probability is what you would expect to happen when events are equally likely to occur. So the first one is, event A is the probability of rolling a 3. So you want the probability of a 3, and a couple of different ways you can actually write out probability rolling a 3, or you could just probability of a 3. The probability of a 3 would be, there's 1 3 on the die. That's the number of outcomes in the event we're talking about. So there's only 1 3 on the die. So that's 1 out of, and then the total number of outcomes in the sample space, there are 6 different possible outcomes. So it'd be 1 out of 6. And then typically they change these over to decimals with 3 decimal places. So that would be a 0.167. Next is the probability of rolling a 7. Since there are no 7s on the die, since it's a 6-sided die, it would be 0 out of 6, which would be 0. So this is an event that cannot happen. When an event cannot happen, or it's not possible, that's always going to be a 0 for your probability. And then the next one is rolling a number less than 5. So the probability of a number less than 5, that would be 1, 2, 3, or 4. So there are 4 out of the 6 numbers that are less than 5. That could reduce to 2/3. And as a decimal, that approximation would be 0.66 repeating. So we do 0.667. The next kind of probability is called empirical or statistical probability. And this is one where you actually perform the event a number of times and you record your observations. So if you were to actually roll the die 100 times and write down what you got each time, you would be looking at empirical probability. It is based on observations obtained from the experiment. So you're actually doing the experiment and recording your events. The probability of an event E is the relative frequency of the event. So how many times when you rolled the die 100 times, how many times did you get a 4? And then, of course, out of the total frequency would be the total number of times that you rolled the die. This can be used even if the outcome is not equally likely to occur. So even if you had a die that for some reason had 2 3s on it and didn't have a 5 on it, then you could still perform the experiment and record the outcomes. So on example 6, it says, we have a company conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year. So we've got 1,409 people, adults surveyed, and the pie chart shows you the results. Note that digital books includes ebooks and audiobooks. So anything electronic is included in digital books. And what is the probability that the next adult surveyed read only print books during the last year? So what we're looking for is we're looking for the total number, which is 1490. If you want to check and make sure, but they told you in the problem, so you don't really have to check it. But if you added 395, 426, 578, and 91, so if you were doing a problem and they didn't give you the total number, you would need to add those up to get the total. So we know that the total number, which is N, is 1490, and we want the probability that the next adult surveyed would have read only print books. So this is going to be the number in the event that we're interested in, which is print books. So read only print books is 578 out of the total number, or the total frequency, which was the 1,490 adults surveyed. And then when you turn that into a decimal by division, you would get approximately 0.388. On number 7, instead of using a pie chart to show us the results, they're using what we call a frequency distribution that we did back in chapter 2. And in the frequency distribution, it tells us how many of each category there are. So the ages 18 to 22, there's 156 of those people. 23 to 35, there's 312 of those people. So the problem here is saying that the company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. The frequency is shown. What is the probability the next user surveyed is 23 to 35? So based on the 975 already surveyed, we want the probability that the age is 23 to 35. And based on this, we've had 312 in that age range out of a total of 975. And again, you divide to get your decimal, and that comes out to 0.32 exactly. And the way we look at this working is something we call the law of large numbers. And so obviously you're not going to be 100% accurate every time. So just because you think that when you flip a coin, you're going to get either heads or tails, so it's a 50-50 shot, that doesn't mean that if you flip the coin 10 times, it's going to land on heads 5 times and tails 5 times. It doesn't always work that way. But what the law of large numbers says is that if you do repeat an experiment over and over and over again, that eventually the empirical probability, so the results of your experiment, would approach the theoretical or the actual probability. So if you only flip the coin 10 times, you might get 8 heads and 2 tails. But if you kept doing it 100 times, eventually it should be getting closer and closer to that 50-50. And that's what the law of large numbers states. Subjective probability is the third type of probability. And this one just is results from intuition, educated guesses, and estimates. So this would not be one that is based on experiments or based theoretically on what you would expect to happen. It's simply based on what you think. So you're making an educated guess, you're estimating, or you're just basing it on your intuition. And on example 8, they ask us to classify each statement as one of the 3. The probability that you will get an A on your next test is 0.9. Okay, this would definitely be an educated guess. It's what you think is going to happen. Maybe you're based it on what the material's covering, and you're like, oh, I really understand this, so I'm going to get an A because this is easy. Or maybe you're basing it on, well, I made an A on the last test, so I think I'll probably make an A on this. But this is definitely an educated guess. So this is subjective. Since you haven't taken the test yet, you don't really have any past experience with it to determine what you're going to make on it. You're guessing that you're going to make an A. On number 2, it's the probability the voter chosen at random will be younger than 35 years old is 0.3. So the only way you would be able to obtain this information is you would have to be surveying to ask random voters what their ages are. So the probability that the voter chosen at random will be younger than 35, you're looking at maybe it's at the day of the election, and you're asking the people as they go in, what age are you? And you're recording that, but you're definitely performing some kind of survey. So since this is some kind of survey, this would definitely be empirical. You're performing an experiment. And then the third one, the probability of winning a 1,000 ticket raffle with one ticket is 1 in 1,000. Well, if there's only one winning ticket out of 1,000, then obviously the only probability that applies here is you have a 1 in 1,000 chance of winning if you only buy one ticket. So this is definitely theoretical. So when you do these, you're looking for, is it an educated guess? Is it based on your intuition? Or are you making an estimate? That's subjective. Is it something that you're actually doing a survey or recording observations? That's empirical. And then is it something that you know the number of outcomes and each one's equally likely to occur? And that's theoretical. And then the range of probabilities rule, and I mentioned this a second ago on the zero, the impossible. The range of probabilities rule says that if something can't happen at all, it's impossible, that would have a probability of 0. And if it's something that's certain to happen, so for example, you're flipping a coin and you say the probability of getting heads or tails, well, every time you flip it, you're either going to get heads or tails, so you're certain to get either heads or tails. That would be a 1. And then all of the probabilities are going to fall between those two numbers. So it says the probability of an event is between 0 and 1 inclusive, meaning that it can be 0, it can be 1, or it can be any number in between. So you write that 0 less than or equal to the probability of the event less than or equal to 1. So if you're working one of these problems and you answer that the probability is 3.5, you've done something incorrectly because you can't have a probability greater than 1. And also you can't have a negative probability. And then we've talked about things being considered unusual, and we talked about that based on the number of standard deviations, and that if it was more than 2 standard deviations, we consider it unusual. Well, in probability, we say that if an event has a probability of less than 0.05 or less, if the probability is 0.05 or less, so that's a 5% chance or less, it's considered unusual or highly unlikely to occur. So if you'll think back to the standard deviations and the bell-shaped distribution, remember we had the 95% of the data fell within 2 standard deviations. So that would mean 5% would fall outside there. So that 5% would be unusual, and that's what they're saying here. If the event has a probability of 0.05 or less, or 5% or less, it's considered unusual. Next, we're looking at complementary events. And when you add up all of the probabilities of outcomes, so if you find for example, rolling a die, again, that's just an easy one to use, the probability of getting a 1, a probability of getting a 2, a 3, a 4, a 5, or a 6, when you add up all of those probabilities, you're going to end up with 100%. So like if you add, there's a 1 out of 6 chance of getting a 1, a 1 out of 6 chance of getting a 2, a 3, a 4, a 5, and a 6, then that would be a 6 out of 6, and which would be a 1, which would be 100%. So on this definition, it says the complement of an event, E, is the set of all outcomes in a sample space that are not included in event E. So this is basically saying, okay, instead of saying what's the probability of getting a 6, then how many of the numbers are not 6? So it's the set of all outcomes that are not included in event E. The complement of event E is denoted with this little prime mark here. And it's read E prime, and that's just the mathematical symbol. We call that prime, E prime. The Venn diagram here illustrates the relationship. So you have a sample space. In here you have all of the things that do occur in event E, all the things that are included in event E, and then outside you have all the things that are not included in event E. So inside the circle, event E, outside the circle, those things that are not included, and that would be E prime. So on example 9, it gives us the frequency distribution that we talked about earlier with the ages. And it says, find the probability of randomly selecting a social networking site user who is not 23 to 35 years old. So when we're looking at this, we did the probability that they were 23 to 35 earlier. And we got that that was 312 out of 975, which was 0.32. So if we want the probability that they're not 23 to 35, that would be everybody else that's left. So one way you can do this, obviously, is to add up the ones who are not 23 to 35. But the quicker way to do it is that we know together those who are 23 to 35 added to those who are not gives us the full group, which was 975. And we know that if we chose all of those, the total probability would be 1. So if you want to get the complement of that age range, or those that are not in that age range, it would just simply be 1 minus those who are in the age range. So 1 minus 312 over 975, which would be 1 minus 0.32, and that would be 0.68. So 68% of those selected were not in the age range 23 to 35. And this will always work when you have 2 events, and one says, what's the probability that this will occur? And the second one says, what's the probability this will not occur? You can always do 1 minus the first event. And then finally here, we're going to look at a couple of applications. On example 10, it says using a tree diagram. And we're not actually going to write out the tree diagram because this one's pretty easy to figure out without the tree diagram, so we won't actually draw it out for the example. So the probability experiment consists of tossing a coin and spinning the spinner shown here at the left. The spinner is equally likely to land on each number, so each of the spaces are the same. Use a tree diagram to find the probability of each event. So event A is tossing a tail and spinning an odd number. So that means that, and I'm just going to write out the sample space. Like I said, instead of creating the tree diagram, I'm just going to write out the sample space. So we want tossing a tail and spinning an odd number. So you could do tail and 1. That would be an odd number. Tossing a tail and getting a 3. Tossing a tail and getting a 5, or tossing a tail and getting a 7. So there are 4 possible outcomes that involve a tail and an odd number. So there's 4 possible. And if you multiply the possibilities, this goes back to the fundamental counting principle. There's 2 possibilities when you flip the coin or toss the coin. And there are 8 possibilities on the spinner. So that means there's a total of 16 possible outcomes. So when I do probability, I have 4 outcomes that involve tails and an odd number out of the 16 possibilities total, and 4 out of 16 would be 1/4 or 0.25. Then on example 2, it's the probability of getting a head or spinning a number greater than 3. So again, we can just list these out real quickly. So you could get a heads, and it says, notice here it says tossing a head or spinning. So that's important. The first one said and, the second one says or. So tossing a head could be heads with 1, 2, 3, 4, 5, and 6. So any of those contain a head, or spinning a number greater than 3. So on spinning the number greater than 3, oops, I didn't go all the way up to 8. I was thinking about the die still. Okay, so we can get anything with a heads 1, heads 2, heads 3, all the way up to heads 8, or spinning a number greater than 3. So on the number greater than 3, it could be heads or tails. So it could be tails and a 4, tails and a 5, tails 6, tails 7, tails 8. So this would be all the possible outcomes that would have either a head or a number greater than 3. Or it could be both heads and greater than 3. But when it says or, it's either heads or greater than 3, and you're adding all those possibilities together. So when you count these up, there's 13 of those, and we said the total possible outcomes was 16. So 13 out of 16 of the outcomes include either heads or a number greater than 3. And this would be approximately 0.813. And then on our final example, your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? So first thing you want to do is how many possible ways can you generate 8 digits? So you have, it's an 8-digit number, and each digit can be anything 0 through 9. So you have 10 choices for each of the 8 numbers. So you would have 10 times itself 8 times, and that would be 10 to the 8th power. Which would be a 1 with 8 zeros. So you would have there are 100 million different 8-digit identification codes that could be created. 100 million. So the probability of choosing your identification code would be one of those 100 million. So the probability would be 1 out of 100 million, which is point, and then we have a bunch of zeros here. And a 1. So 0.000000001. That would be the probability of choosing your college identification number at random.